Good evening. My name is Shehryar and I'm a PhD candidate in mechanical engineering working under the supervision of Professor Norman Joe and Professor Elliot Birrell. My core research focus is on the advanced joining of coated high-strength steels and other metallic alloys used in the automotive industry. The title of this short presentation is The Role of Graphite and Carbide Nanoparticles on Ferrite Phase Suppression in 22 Mn B5 press-hardened steels. There is an overwhelming demand to improve the safety and crashworthiness of our vehicles, while at the same time reducing vehicle weight in order to improve overall efficiency. There are two main ways of meeting this demand. The first is to increase the usage of advanced high-strength steels in body-in-white frames of vehicles, which has almost quadrupled in recent years. The second is by making use of vehicle components that have tailored properties, which can be achieved by employing tailor-welded blanks, which are manufactured by joining different types of press-hardened steels using laser welding, and then hot stamping the welded blank to make the component with the desired geometry, shape, and mechanical properties. Hot stamped tailor-welded blanks offer several benefits, such as weight reduction, part consolidation, and improved part performance. Now, 22 Mn B5 is the most commonly used grade of steel for the production of tailor-welded blanks because after the hot stamping heat treatment, the steel exhibits a tensile strength of about 1500 megapascals and a yield strength of about 1100 megapascals as shown by the flow curves. During hot stamping, the material is heated in a furnace to about 930 degrees Celsius for about 5 minutes, followed by rapid quenching of the steel with a water-cooled dye for about 5 to 10 seconds. The typical morphology of the material in the hot stamped condition is that of lath martensite. Now, as with most steels, surface oxidation is a significant problem for 22 Mn B5 steel, as oxide scale formation occurs immediately at the elevated hot stamping temperatures. So the use of a coating to protect the steel helps to avoid surface oxidation and decarburization, and it has been shown that the aluminum silicon coating is the most effective coating for hot stamping applications. However, during the laser welding of aluminum silicon coated 22 Mn B5, the coating is diluted in the weld zone according to the Marangoni convection flow, as can be seen by the cross-section AA. As the molten coating flows into the weld, the extremely high cooling rate during laser welding causes the aluminum to become entrapped along the fusion boundary as the weld pool quickly solidifies. This leads to the formation of a dual-phase microstructure in the weld, with a network-like delta ferrite phase embedded in a martensitic matrix. Now, what are the implications of a dual-phase fusion zone on the mechanical properties? Well, to answer this question, we must consider the differences between the two phases, the most important of which is the fact that the martensite phase is significantly harder than the ferrite phase, clearly showing that the weld fusion zone is much softer than the bulk material. The softer fusion zone significantly reduces the load-bearing capacity of the joint, and the joint efficiency is about 74% of the base condition, which is extremely poor and happens to be a huge problem from a safety and crashworthiness standpoint. So the first main objective of this research was to investigate the microstructural welds produced during fiber laser welding of aluminum silicon coated 22 Mn B5, while characterizing the metallurgical and mechanical issues observed in these welds. The second main objective was to investigate the effect of colloidal graphite and carbide nanoparticles on the mechanical and metallurgical properties of these welds. Specifically, we will be investigating the phase transformation mechanism that retards the formation of ferrite with the addition of graphite and carbide nanoparticles, while simultaneously investigating the strengthening mechanism promoted by the addition of carbon-based nanoparticles. And with that, we come to the end of this presentation. Thank you all for your attention.